Welcome back to our last talk of the day. The next speaker is Antoine Boivin from the Universite d'Angers with his talk titled Non-Simplicial Quantum Toric Varieties. So, Antoine, go ahead.
Okay, thank you for the invitation and for the opportunity to speak here. My talk will be about the construction of quantum toric varieties associated to a non-simplicial fan, as explained in my paper, Non-Simplicial Quantum Toric Varieties, submitted to arXiv in June of this year. This paper is heavily based on the paper of Ludmil Kaczorkov, Ernesto Lupercio, Laurent Mersman, and Alberto Veroschi, Quantum Non-Commutative Toric Geometry. The goal of this paper, as Ernesto said, is to extend the dictionary between the combinatorial data of a fan on a lattice on the geometric properties of the toric variety to the case where we have a simplicial fan on a finitely generated subgroup for RD, as known as quasi-lattice. In other words, there is an equivalence of categories between the fan on a finitely generated subgroup of RD on the category of quantum toric varieties, which is some kind of stacks. This functoriality is used in order to compute moduli spaces of toric varieties. By example, in R2, if we take 3 rays, we get projective plane or weighted projective plane in rational case. And in general, the moduli space of a projective plane is given by R minus times R minus modulo the action of the symmetry group on 3 objects. We can remark that this modulo space is an orbifold, but is not proper. Hence, a natural question to ask is how compactify it in the same way that we compactify the moduli stack of smooth curves of given genus by adding the nodal curves. So in our case, this question leads to the study of non-simplicial fans, where the one cones of the cones in this fan can be not a basis, form not a basis of the ambient space. So in classical theory, the difference between simplicial or non-simplicial toric variety leads to the allowed singularity. Indeed, in classical theory, we have the simplicial fan correspond to the orbifold toric varieties, which is a toric variety with cyclic singularities. But in the simplical case, we can have more complicated singularity. An example of it is the cone of a quadratic surface in C4, which is toric, but not orbifold. Now I will give some picture of the combinatorics of non-simplicial cones. So firstly, these non-simplicial cones exist only in dimension at least 3. In dimension 1, there are 2 cones, the positive ray and the negative ray. In dimension 2, given a set of rays, we can define a fan where maximal cones are delimited by 2 rays, like we can see in this picture. So we have a cones here, a cones here, 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 and here. So we can see that we have only simplicial cones. There are 2. There are one rays, then the rays from the basis of R2. So there are no non-simplicial cones in dimension 1 or 2. But there exist non-simplicial cones in dimension 3, like we will see here. So the second feature of non-simplicial cones is that they can have an arbitrary number of 1 cones. A way to build it is we take an integer n. We can consider the n-gon in R3 in height 1 and build the cone generated by the vertices of this n-gon. Like in this picture, we have n equal to 5. So So we take it in height 1, and we go from 0 to the vertices of the n-gon and go in infinity. So we can see that this cone have 5 one-cones, which is bigger than 3. So yes. So the third features of non-simplicial cones is that the fact that they don't have a nice description of their faces. Indeed, the faces of simplicial cones are generated by the subset of the generators of the cone. But it's not the case for the non-simplicial cones. Let's see an example. We take the cone generated by E1, E2, E3, the canonical basis of R3, with the fourth vector V equals to E1 minus E2 plus E3. We have some picture here. So we can see that the faces of this cone, the faces with one generator of this cone are, as expected, the cone generated by E1, by E2, by E3, by V. But the cones with two generators, there miss 2 of them. The cone generated by E1 on E3, and the cone generated by V on E2. The problem here is that we have a cone between them. Here we have V, and here we have E3. On this cone have not cones with 3 generators. No faces with 3 generators. It's due to the fact that such faces have to be dimension 2. But as I said before, the cone in dimension 2 are simplicial, so it can have 3 generators. So in conclusion, the combinatorics of non-simplicial cones, it's a bit harder than the simplicial one. In order to finish my introduction, I will recall some definition on quantum toric geometry. Firstly, I will give some definition on the stacks considered in quantum toric geometry. So in the first part, we have to have a site. This site is the underlying category of this site, the category of affine toric varieties with toric morphism, which is morphism of variety which restrict to a torus morphism or algebraic group morphism. And when we have a category, in order to have a site, we have to give this category a quotient topology. So it can be achieved with coverings. So covering of a toric variety X is given by toric open subset of X, UI, such that their union is X. Now we have a site, we can define stacks. So in quantum toric geometry, we have 2 kinds of stacks, the quotient stacks and the descent data of them, given by the descent data of them. So we will consider the quotient stack. You take toric variety X and an abelian Lie group H acting on it. This action can be as we want, but the quotient stack X mod H is given by this object over an object on object T, so an affine toric variety given by H principal bundle T tilde to T on H equivariant map between T tilde and X. This T tilde is not a toric variety, since the problem here is that the product of a toric variety with an abelian Lie group can be not a toric variety. Think of the case where H is the group Z, which so the T times Z is not a toric variety. On morphism over morphism T to S is given by this commutative diagram. Now we go to the definition of quantum toric geometry. So if we take finitely generated subgroup of RD gamma, which contains ZD, a calibration of this group is an epimorphism H from Zn to gamma. With this condition, it will be used in order to give a multiplicative form of for the quantum torus on a subset I of 1 to n with that condition. This subset will be the set of virtual generators of the calibration. So now we have a calibration, we can define a quantum torus associated to it. It is a quotient stack defined by the quotient of CD by the action of Zn, given by the calibration H, like that. And now we have object. We want some morphism in order to define a category. So a morphism of quantum tori is given by two linear maps, L and H, with a map between the sets of virtual generators. And we want to that these three maps are compatible with the calibrations. This definition is given in order to have a stack morphism between the associated quantum tori. And finally, as promised, you can define a multiplicative form of the quantum torus, which is the quotient of the algebraic torus C star to the power D by the action of some Zn minus D, which is defined multiplicatively. So we have an exponential map here, and it's an exponential map to I pi's in order to give a kernel, in order to this map have a kernel Z to the power D. And this quantum torus will be the torus associated to the quantum toric varieties in the quantum case. So now I have given some definition. I will go to the plan of my talk. Firstly, I will present you the presented quantum tori. As said before, the non-simplicial cones can have an arbitrary number of one cones. Then we have to have a good notion of torus in order to manage its behavior. After that, I will present you how build affine quantum toric varieties with a cone on the a group on calibration. And in the last part, I will define global quantum toric varieties on how to compute them in an effective way. So firstly, the presented calibrated quantum torus. So it's a standard quantum torus given by a calibration on the data of a stack isomorphism with an higher dimensional CP, where the P here is will be the number of one cones of the considered cone. And more precisely, we have phi I prime, which is a calibration of a group gamma G isomorphic to the group gamma. We have two linear maps, L and H, which is with encode the stack isomorphism, and S will be a set between the map set between the set of virtual generators. So the morphism phi will be the calibration of this presented calibrated quantum torus. And we can do some remarks on this definition. So if P equal to D, here, since L is a linear.
Sorry, could you remind me, please, what is gamma?
Gamma is a finitely generated subgroup of RD.
Okay, thank you.
yes, if P equal to D, so this linear epimorphism is an isomorphism. So this data L on H on S define a torus isomorphism between the torus given by the calibration hashed I prime I on the quantum torus given by the calibration phi I prime. And in the general case, they define a stack isomorphism between the torus given by H on I on the quotient stack Cp mod Zn times the kernel of L, where Zn acts on Cp by the morphism phi, and the kernel acts by the identity on Cp. So we can define morphism between presented calibrated quantum tori, which is a torus morphism between the quantum torus given by the H on I, on H prime on I prime, with morphism compatible with the data of the presentation. So here, this morphism is a stack morphism between the associated stack. So it's L prime. The compatibility with the data of the presentation makes this diagram commuting. So the isomorphism are the isomorphism given by the presentation, like I said here. And LCal is a torus morphism of this definition. Unlike the standard case, there exists a multiplicative form of associated stack, which is we replace Cp by Tp, and we make the exponential in the group where we mod out. So okay. So the principal facts on this presented quantum tori is that we don't make new quantum tori. Indeed, if we consider the forgetful functor, which forget all the presentation here, this functor is an equivalence of categories between the category of presented calibrated quantum tori and the category of standard calibrated quantum tori. So presented quantum torus is just a quantum torus described in another way. Now, since we have defined the tori, we can define affine quantum toric varieties. So I will give you the setting. So we have a finitely generated subgroup gamma of Rd, which contains Zd, a calibration H scale I of this group gamma, on a strongly convex cone, sigma of Rd of dimension d. So the dimension of the cone is given by the dimension of the vector space generated by this cone. And it's generated by some Vi given by the calibration. Here you can remark that this index set I will not meet this virtual generator, since it's the properties of this set. So with this data, we will construct a calibration adapted to the cone sigma. So we can define an epimorphism H sigma, which is just the restriction of calibration of Ci, which the I is I here, it's the same I. So we can mark a thing, is that this morphism is an isomorphism if only if I is equal to D. And it's the case, the cardinal of I is equal to D, which is the case if only if sigma is simplicial. Now we can make a decomposition of Ci by the kernel of H sigma plus some complement vector space given by the canonical basis. So we have Ci tilde. We can remark that this, if H sigma C sigma is simplicial, then this kernel is trivial. So we have Ci equal to Ci tilde, and then we can define a permutation K of the symmetric group on n object, such that the image of the first integer is I tilde. So with all of that, we can define a morphism with this formula. This morphism goes from C to the power n to Ci, and is called the calibration associated to sigma, the basis B, on the permutation K. The feature of this morphism is that they send the Z to the power D in Cn to Z to the power I tilde. You can do the computation if you want. So now, in the same way as the tori, we can define an action of this group on Ci. By this thing, you can see the morphism file. And we define the quotient stack associated to it. So it's Ci mod this action. We can remark that this stack doesn't depend on the decomposition nor on the permutation, since if we change these two things, so we take another decomposition on another permutation, we have a unique equivalent automorphism of C to the power I, and first a unique stack isomorphism between the two possible stacks. Then this definition makes sense. The stack U sigma is a quantum toric variety associated to the cone sigma on the calibration HKL. So we can also define presented quantum torics with all the data previously defined. So we have phi on the permutation of the virtual generator of the first calibration. You have H sigma and two isomorphism. So this presented quantum torus encodes the stack Ti modulo the action of this action.
Sorry, I missed your definition of sigma, the cone. Was it combinatorial? I really missed it in the.
Here.
I don't know where it was. But never mind. I just wanted to ask if big N is bigger than the number of rays of any cone you can consider.
Yes, because we have some virtual generators, which is not in the rays of the fan.
Okay. Okay. Thank you.
Okay, so I was here. So, okay, since we have the construction, we can go to an example. Example, yes. So we have, we consider the morphism HK given by this thing. So the first E1, E2, E3 is sent to E1, E2, E3 in R3. E4 is sent in a vector of R3, and the other EK is sent to VK, which will be the virtual generators of the calibration. And we define gamma as image of HK. So by co-restricting the morphism HK, we get a calibration of gamma. And we take a cone sigma given by E1, E2, E3, and we have a picture there. So H sigma The kernel of H sigma will be given by this line, generated by the vector v minus 1. And we can define a decomposition of C4 by C3 times 0 plus this line. So the cone encodes an action on C4, given like that. And we can define the quantum toric variety associated to sigma with the quotient of C4 by this action. In order to finish my example, I will say a few words on the stabilizer of this action. All the points of C4 are stabilized by the kernel of H scale, since if lambda here is 0 and m is in the kernel, all of that is 0 and the exponential is 1. So it doesn't move z. And we can find bigger stabilizer on C3 times 0 and on the kernel of H sigma. And the biggest stabilizer is on 0, which is the whole group. Now I will give you some links with this construction with some other constructions. Firstly, with the classical setting. So we take gamma a lattice, and the calibration is an isomorphism, and the set of virtual generator is empty. So the U sigma is not representable by a variety nor scheme, and so a fortiori is not isomorphic to the toric variety U sigma, but we can found the classical toric variety U sigma by taking the GIT quotient of Ci by this group. So we can do a remark that if gamma is a lattice and H is a calibration, n equal to D, so there are no Z part. And for the links with the quantum toric variety, so we take a general gamma, but with a simplicial sigma, and we have a toric isomorphism. And a toric isomorphism is a morphism of stack between the toric variety with which sits on the quantum torus as a morphism. So we have a toric isomorphism between U sigma and the construction of Karsakov and all. The key point here is that H sigma in the simplicial case is the kernel of H sigma is empty, but it's trivial. So there are no exponential part here. So we have only the Z part, like here, and it's isomorph. It's the same action, but with up to a rearrangement of the with a permutation between I and D. The biggest problem here is that in this quotient, GIT quotient here, we have some semi-stable point which is not stable. So the GIT quotient is not a geometric quotient. So we can't have the representability of the U sigma. Now I have affine quantum toric varieties. So I want to glue them in a general toric variety. So in order to do that, I want to define quantum toric variety associated to a face of a cone.
Can I ask a little question? Can I, in the previous slide? They are certainly non-isomorphic at all. But is there a forgetful map from one to the other? It would seem to me that the curly one has a little bit more information than the non-curly one at first, a priori. but then the one at the top has a little bit more information than the GIT one. But then I don't know if both can be recovered from the other or not. In any case, there should be a forgetful map from one to the other. No?
So yes, you have more information there, since we can extract from there a stable locus, I think, a stable locus of the action, or you can find the GIT quotient like that. But
a counterintuitive question is whether you could recover the top from the bottom.
yes, I don't understand the question. So,
well, from the curly one,
yes,
from the stack, you can recover the GIT one.
Yes.
No problem. A more counterintuitive question is whether you can recover the stack from the GIT one.
I think not, but I don't know.
Can you recover the cone and everything from the GIT one?
If you have the group on the toric variety, you can recover the curly one, I think, but I don't know if we can do more of it.
Yeah. Well, it's just a question. It's just an interesting question. How much you can recover from one from the other?
Yes, in order to close the affine quantum toric variety, you have to define quantum toric variety associated to a face of a cone. There are two possible ways to do it. The first way is defined as an open substack of the quantum toric variety associated to the bigger cone. And another way it's done as follows. So you have a face tau of dimension less than d. You choose the complement of the vector space given by the face tau with some VG given by the calibration. And now we have epimorphism. Here it's a restriction of the calibration on the space Ci times Cg. So we can do the same construction of the maximal dimension case, and we get affine toric variety here. So in order to stress the fact that this face is not maximal dimension, we replace the C here by a T. So T is the torus C star. And we can ask if the choice of G is important. So if we change this family, we get an isomorphism between the two obtained stack. And here it's a tau. And this isomorphism respects the co-cycle condition, so it's not harmful. But we have two possible constructions, but the good news is that these two constructions are isomorphic. And this isomorphism respects the torus, the tori, like you can see there. Now we can go to the general case. So we have all the things to make the gluing. So we take a finitely generous subgroup gamma on a calibration of it. And we take a family of strongly convex cones sigma of RD, such that every intersection of cones is a cone, and every face of a cone is a cone. These two conditions induce transition map between the affine quantum toric varieties with intersecting cones. This data is called a quantum fan. And it's called extended stacky fan in the rational case. So we can define the quantum toric varieties like that. So a quantum toric variety associated to a quantum fan is a stack defined as a descent data of the affine quantum toric varieties. In other words, an object of x over t is given by a covering of t indexed by the maximal cones, delta max, with, for each ti, an object of u sigma I over ti, like that, verifying, satisfying this condition. So the GII prime is the transition map given by the intersecting cones. So we want all of that is compatible, and we have the good definition. So it's natural way to define a stack, since by definition in a stack we can glue the object of morphism of over some objects. So okay, we have the definition. So we can go to the main theorem. So the theorem of Karsarkov, Lupercio, Mersmann, and Tarowski, it's that correspondence between the quantum fan, calibrated quantum fan delta h scale I to the quantum toric variety is functorial. So it sends the morphism on object on object. And, okay, and it's induced an equivalence of categories between the category of simplicial calibrated quantum fan and the category of simplicial calibrated quantum toric varieties. So the main theorem of my paper is to extend this equivalence of categories to the case where we have arbitrary calibrated quantum fan on the construction of calibrated quantum toric variety, as I said you before. Consequently, the moduli space of quantum toric varieties can be fully described with moduli space of fans, of quantum fans. Yeah, we can remark that now we want to do some computation. So we can remark that this definition is very beautiful, but we can do computation. We can't do computation, so we have to make some further computation. So in classical theory, a toric variety can be described as a GIT quotient of an affine toric variety by a torus. And in quantum toric geometry, a calibrated quantum toric variety is isomorphic to a quotient of a toric variety by an action of c to the power n minus d, which is a quantum GIT. I explained this in the last part of my talk. And so let's see what can we get in the non-simplicial case. So we begin with the quantum fan, delta h scale I. So
sorry again. Could you? Sometimes I lose the notation. What is I here in the definition of quantum fan? Yes.
It's the set of virtual generators.
Okay, thanks.
Okay, so we can associate this fan of Zn whose maximal cones on that fan are given by the pullback of the maximal cones of delta along the morphism H scale. And we can define a classical toric variety associated to this fan, S. We can remark that this variety S is the same in the two previous cases. So in the classical theory, we want to do a GIT quotient of S, and in quantum toric geometry, we want to quotient this toric variety by the action of Cn minus d. So we can prove that the quantum toric variety given by this quantum fan is isomorphic to the quotient of S by this group. And the action of this group on S is defined in the same way as the affine quantum toric variety if we replace H sigma by the global, the whole calibration. And this isomorphism is an isomorphism, a toric isomorphism on each affine chart of X-cal. And it respects the torus as a tori. So now with this theorem, we can do computation. So I will give you a second example. So I take an epsilon positive, a vector v given like that, on a group, which is Z3 plus ZV in R3, a calibration of this group, and the fan of R3 given by this cones.
Mm-hmm.
So okay, so we have 6 simplicial cones. There are 2, 4, 5, 6, on 1 non-simplicial cones. On this picture is it's a polytope associated to this fan. So the face of this polytope is a maximal fan of a maximal cones of this fan. And this polytope is a dual polytope of some deformation with epsilon of the transition polytope of the flip of type 2,2 of the cube. In other words, we choose 2 faces of the octahedron, which is a dual polytope of the cube, in order to have a non-simplicial polytope on a non-simplicial fan. Here we have 4 edges. On the quantum toric variety, as described by the quantum fan delta H scale on the empty set of virtual generators, which is the quotient of the toric variety S, given by this formula, by the action of this group in the same way as affine quantum toric variety. We get this toric variety in the following way. So this part is toric variety given by the octahedron. Then we remove 2 faces we want to fuse, and we add the fusion of them, as the variety associated to the fusion of them. So we have easy example of computation. Now I will go to the quantum GIT quotient. And in the first part, I will recall what is the Gale transform. So we have, for the Gale transform, we have a family of vectors of Rd, V1 to Vn. And a Gale transform of this family is given by a family of Rn minus d with the same cardinal. And these 2 families define 2 morphisms. So H is a linear combination of the element of the first family. The morphism K is given by the inner product for each point of each vectors of Rn minus d. And the condition of Gale transform is that this sequence is exact.
Sorry, does it coincide with the calibration, or has nothing to do?
Yes. H will be the calibration,
Okay.
but I give the general statement.
Sorry to interrupt.
Okay, we have the Gale transform. So the quantum GIT theorem given by Karp, Sarkov, Lippershey, Mersmann, Berowski is quantum fan is simplicial. The quantum toric variety given by some quantum fan can be described as a global quotient of the toric variety S, which is the same as before, on modulo the action of C to the power n minus d, which acts on S by the exponential of the morphism given by the Gale transform. And we take the Gale transform of the family of points given by the calibration. So this family. On an idea of proof of this theorem is we can prove that if we take the open substack of the quotient here given by cones, so we give the index of the cone I, and we take Ci times T to the complementary of I, and we can prove that this stack and the quantum toric variety associated to sigma I are isomorphic. So in each affine pieces we have an isomorphism, and by functorial directive we can glue the isomorphism on global isomorphism between the quantum toric variety and the GIT quotient, by quantum GIT quotient. But if I write simply, if the quantum fan is simplicial, it's not the case. It's because it's not the case if the quantum fan is non-simplicial. Indeed, the stacks U sigma and the stack U sigma prime here are not isomorphic if sigma is not simplicial. And we can prove this by checking the stabilizer of the two actions. Indeed, the stabilizer in the quantum GIT case is of the form C to the power K. And the stabilizer of the affine quantum toric variety U sigma is of the form Z to the power K times C star to the power K, which can be isomorphic due in particular of the torsion. And since the stabilizer are not isomorphic, the groupoid associated to these two quotient stacks are not isomorphic, are not Morita equivalent. So the stack given by this groupoid can be isomorphic. And in the natural question to ask is can we do the converse? Can we define the quantum toric variety as a quantum GIT quotient? And we can't, because owing to the presence of non-simplicial cones, we can't. We have in the same manner that we haven't isomorphism between the quantum toric variety and the quantum GIT. The affine pieces would have not non-isomorphic torus, which is a bad behavior of quantum toric variety if we define it like that. So it's because it's the reason I define quantum toric variety in the other manner. Thank you for your attention.
Very good. Thank you so much.
Well, thank you, Antoine. Somebody have any question?
So just to make sure I have well understood, so the fan doesn't need to be polytopic, right?
Yes.
Any simplicial, any fan actually.
Yes.
Okay,
actually.
thanks.
Well, thank you very much.